Hello, everyone, and welcome. My name is Liz Kemper, and I'll be your moderator for today's WJE webinar, Findings of Low-Rise Foam Adhesive Testing Program. During the next hour, WJE roofing experts Patrick Shaughnessy and Richard Koziel will provide an overview of the research and testing program, summarize the results, including installation factors found to have a greater impact on overall bond capacity, and discuss the impact of this research on the design, specification, and construction of roofs. This presentation is copyrighted by With Jenny Elson Associates. And now I'll turn it over to Pat to get started. Pat?
Thanks, Liz. I want to thank everybody for joining us today. We did some pretty interesting testing, and I think all of you will find it interesting as well. So by the end of the presentation, you should be able to summarize the testing methodology and results that were used for the low-rise foam insulation adhesive testing, explain the differences between the various ribbon spaces for the different types of insulation facers that are common in the industry, identify the failure mechanisms of the facers in regard to wind uplift strengths, and describe insulation techniques that can help achieve optimal performance in roofing systems that are adhered using the low-rise foam adhesives. Goals of today's presentation are to, one, provide an overview of the Midwest Roofing Contractors Association's research project. I will be referring to the Midwest Roofing Contractors Association as the MRCA for the duration of the presentation. And then also, we will summarize results of the testing that was conducted on the insulation that was adhered with the low-rise foam insulation adhesive. And then finally, at the end of the presentation, we will take questions. So before we get too far, I want to make sure that everyone has a basic understanding of the components that are typically included in a roof system. I know that there are a lot of you out there that this may be some basic knowledge, but I also know that there's some people out there that may not have as much knowledge about roofing systems as everybody else. So starting from the bottom up, we have our roof deck. Pictured here is a metal roof deck. Other common types of roof decks that you'll run into are going to be concrete, wood will be a little more prevalent out west and in the Northwest. Then there's some specialized roof decks, such as gypsum or Tectum panels. Typically run into those in retrofit roofing construction. Then over that, we have our first layer. In this slide, we're showing a thermal barrier or a substrate board, which is commonly used with a metal roof deck, and then that's mechanically attached to the roof deck. And then you'll see the low-rise foam adhesive, which is basically the crux of what we're talking about today, applied in what we call ribbons, or lines of adhesive that are at predetermined spacings. So that's installed on top of this substrate board, and then over that goes our first layer of insulation. We'll be referring to the insulation as polyisocyanurate or polyiso insulation that was used for the testing. It's a rigid insulation board that has what's called a facer on the top and bottom, and the sides, the foam core is visible. And then over that, we put more adhesive ribbons, and then common in today's roofing construction, there's going to be multiple layers of roofing insulation. So we set that material in the adhesive and try to achieve it where we have the joints from the top layer and the bottom layer offset from each other to reduce air movement within the roofing system. And then over that, commonly we'll see what's called a cover board, which is a high density material that helps give the roofing system impact resistance to protect things are inadvertently dropped on the system, or even offer some protection during hail. And then finally, over that, we install our roofing membrane. In this picture, we could have a PVC, a TPO, or even an EPDM single-ply roofing system. There are other systems out there, such as a 4-ply built-up asphalt or multi-ply built-up asphalt. commonly referred to as like a tar and gravel roof or a modified bitumen roof membrane. So kind of your roofing 101, what the components are. We will be really concentrating in this presentation on those 2 layers of polyisocyanurate along with those ribbons of adhesive. Little background on how we got to where we are. The MRCA issued a request for proposal in May of 2019, and it was kind of prompted because of issues that some of their member contractors were having with consultants regarding rates of application of adhesive. It being performed by a human, so there's a little bit of variation in the spacing, and sometimes it's a little less than perfect. So that was kind of what was the impetus behind everything. In the MRCA request for proposal was a problem statement, and it was really the heart of the research that was completed, and that read, what impact does variation in foam ribbon spacing have on ultimate roof uplift capacity? Also in the RFP, MRCA had some initial thoughts on what they thought would be the basis for the testing. They wanted to have in the low-rise foams testing, full-scale testing of full-size samples. Full-size boards being 4 foot by 4 foot boards that were 2 inch thick. There are 4 foot by 8 foot boards out there, but those are commonly only used in a mechanically attached type of situation. And in many scenarios, adhering those boards is not permitted by most roofing manufacturers. And then we'd be using the two-part foam urethane adhesive applied in ribbons at various spacings. Currently, the industry standards are 4 inch, 6 inch, and 12 inch spacings. So what is the value of the testing program for the MRCA? There's little information on how slight spacing irregularities and variances affect the ultimate bond of the insulation layers, and little information about how the issue of spacing and how that correlates with and how it affects wind uplift properties of insulation. So we met with the MRCA Technical and Research Committee, taking their information and then figuring out how to best address the problem statement that they came up with in their RFP. And so what we came up with was that we would focus strictly on insulation to insulation adhesion. We weren't going to look at the adhesion of insulation to roof decks, to vapor retarders, and we're going to look at roof membrane adhesion to insulation, strictly insulation to insulation. We would use the 4 foot by 4 foot specimens, and then we would use ribbon spacings that were at 6, 12, and 18 inches. 18 inches isn't a normal spacing, but you'll see later in the presentation why we chose to go with the 6, 12, and 18 inch spacings. And in order to test the full 4 foot by 4 foot specimens, it would require that a custom loading apparatus be developed that could accept the full size specimens. There's testing out there that was done on 2 foot by 2 foot samples, but 4 foot by 4 foot is not a common material size to use for testing. And then to go along with the full size samples, we used some companion specimens, and those consisted of some smaller 1 foot by 1 foot insulation samples. And then we also tested adhesive only without having any influence from the insulation board's insulation facers. It was strictly adhesive to adhesive. Then finally, at the end of the testing, we would prepare a comprehensive report that would deliver our findings. So, following the research methodology, the polyisocyanurate insulation was used. We used the two type of facers that are common in the industry. You have your glass fiber reinforced cellulosic felt facers, or sometimes people refer to those as paper facers. And then we had our polymer-coated glass fiber mat facers. Again, 2-inch thick boards, very common thickness that's used in the industry, and then that 4 foot by 4 foot dimension on the boards. And then the adhesive that would be used was a 2-component low-rise polyurethane foam adhesive. All the materials that were used in the presentation were sourced by a single manufacturer, so their guidelines for application were followed when we were putting the sampling together for the testing. So test specimens would basically consist of 2 layers of insulation that were adhered with the low-rise foam insulation. Those would be bonded to plywood backers, and then the samples would then be attached to a large loading frame using T-nuts and metal threaded studs. So getting into the test specimen fabrication here. So you see here the 4 foot by 4 foot plywood backers that were used for the fabrication of the samples. We would adhere the insulation to those samples. And then on the samples, we had preset spacings that were used, and those spacings were laid out in a symmetrical layout. Here, we'll get the video here. Okay. Here's a video of the samples being assembled. We're putting the adhesive onto the plywood and then setting the boards into that adhesive. The adhesive was put on at a rate that would basically give us full coverage of adhesive for the boards to be set into, and then over that, weighted buckets were placed to embed the insulation boards into that adhesive. After the initial foam rise, then we would place the boards together. Here's a slide of that, a video of that. We had an experienced MRCA installer applying the ribbons, and they were trying their best to achieve the 3/4 inch to 1 inch ribbons that are commonly required for installation of the boards. And it will show the video again. So here we are at 6-inch spacings. Second video here is of the 12-inch spacings that we used. So after we have one more with the adhesive being applied here. So the boards were placed on top of each other and then weighted down with weighted buckets. And these buckets each weighed 26 pounds. 26 pounds was chosen because manufacturer recommendations were to use a bucket of adhesive that would be used to adhere the roofing membrane to the insulation, and taking the weight of those buckets into account and then subtracting the weight of the plywood, we came up with 26 pounds for each one of those buckets. So in this slide here, we have a completed test specimen. So here you see the ribbon of adhesive, got a nice spread on it, and that's due to placing the buckets on top of the samples that allowed the material to, for lack of a better term, smush itself and get wide adhesion there. And then up in the upper right-hand corner, we have our 3/8 inch metal studs that were screwed into the T-nuts that were installed prior to installation of the insulation board onto the plywood. Some of the key test considerations that were made were the standard before what we performed here was that 2 by 2 foot samples were used, and MRCA desired to have 4 foot by 4 foot samples. So we knew that in order to perform the testing on the 4 foot by 4 foot samples, we would have to come up with a custom stiffen load apparatus that could apply the load as required. And in order to get proper test results, we needed to apply direct tensile force to the adhered specimens. That loading onto the specimens needed to be uniform. There couldn't be any eccentricities. We couldn't peel from one end or pry. We wanted a completely uniform load over the entire board. So here you see we have a test frame pulling the load in, from the top and from the bottom in equal amounts, and that was achieved with a custom stiffened aluminum load frame. Here's a plan view of the conceptual test apparatus at the left there. So it was a 1/2 inch thick aluminum plate that was used, and then with plenty of stiffening that was welded onto the frame. In the upper right there, that's a section view through the apparatus, which shows the centrally placed loading yoke that would be used to connect the frame to what was going to be applying the force to the samples. Then finally, down the lower right-hand corner, we have how the frame was connected. That's again with the plywood backers that had the T-nuts installed, and then the 3/8 inch threaded rod. Here's a picture of the final apparatus. You'll see the loading yoke there in the center that allows for unimpeded movement in all directions. 1/2 inch load frame, and then the T-nuts with the threaded studs. We use wing nuts to fasten those. You'll notice in this picture we have some galvanized washers that were used. This photo here was a picture that was taken on a test run, and we found that the galvanized washers couldn't stand up for the load that was being put onto the sample. So you'll see in other pictures that we actually switched those out for something a little more substantial. So the samples were then attached to this reaction frame, and the reaction frame at the top had the hydraulic ram, and that's how the pressure was, or the load was put onto the samples in the frame. That was mounted up on top of a reaction beam, and then there's our sandwich down below with the upper load frame, lower load frame with the test specimen attached to both sides of that. And then there's tie-down legs, and then all that assembly is all fastened in through our reaction floor in our lab. So here's a picture of the actual system that was used. This was actually left over from a previous project, and it had a rating of 2 million pounds. So we felt that this would be adequate for the testing that we were going to be using on the insulation samples. But so you see up top, there's that hydraulic ram, and then that connects to the samples through a cable that was brought down through that reaction beam there, and the two sides of the frame, and with the test specimen, and then you see the tie-down legs. So the sample and the tie-down legs are completely independent of the whole frame there, and all this is attached through this the reaction floor that's in our lab, which is a 18-inch thick concrete, heavily reinforced. So you see the threaded rod there that's going through the frame there, and then it's attached on the underside in the basement. Here's a video of the samples being placed onto the frame there. So you'll see they're lining up those threaded rods with the holes in the bottom. and then the upper portion was is lowered down over where those threaded rods are, and then attachment of the samples to the upper and lower frame was achieved with wing nuts. We just hand tighten those so as not to create any deflection in the plate or in the frame. So after the specimens were attached into the frame, then we had some instrumentation that was attached to the specimens, and we used displacement transducers. We had one that was placed at the middle of each of the 4 sides, and then there were 2 additional that were placed in the upper frame near the loading yoke. So the 4 that were placed on the sides would let us know if we were maybe getting some peeling or if any irregularity like that, and then the ones near the yoke would let us know if we were getting any deflection in the testing frame. So there was no standard to test the full size boards in the manner that we did. So we looked to a couple of other procedures out there that were established as inspiration for what we performed. And so we looked at the ANSI SPRY 1A-1 as well as ANSI FM 4474 as a basis for as a starting point for how we wanted to perform this testing. Big differences. So these 2 standards use 2 foot by 2 foot specimens, whereas we were using the full size 4 foot by 4 foot insulation boards. And with our reaction frame loaded or independent from the sampling, we had no reaction forces that would have any effect on the testing of the sample, whereas with the 2 methods from ANSI SPRY and ANSI FM, there could be a little bit of influence from the apparatus being placed on the deck that surrounds the sample area on what the final load would be. So following those 2 standards, we did set the procedure as tested it in increments. So we would start at 30 pounds per square foot plus tare weight, and then we held that for 1 minute, and then the load would be incremented from there at 15 pounds per square feet, and then we would hold it for 1 minute. This would be then repeated until we reached failure of the specimen. Here's a video of testing in action. You can see the boards are separating there at the corner a little bit, and so this is the hydraulic ram being controlled. We would hold that pressure for a minute, and there's the instrumentation that we would view. At the left-hand side, I'm going to replay this. I want to show the instrumentation there. So here we are at the corner. It's opening up. It's separating a little bit. So on the screen that you will see in the lower left-hand corner, that's the actual load that's being put on the specimens in pounds per square feet, and then on the right-hand side was the measuring for the transducers. Here's a failure within the foam core, and then we had a failure at the insulation face of it. So that is how we got to where we tested the insulation samples we assembled and how we got to the testing. So here's Rich to describe the results of our testing and our findings.
Okay, thank you, Pat. So before we get into the test results, I just would like to mention that we developed a naming convention for the samples. We used the letter A to designate polymer-coated glass fiber faced insulation, and the letter B to designate cellulosic felt facer. So in this image, you can see it's the test sample there is A182. That would mean A, or the polymer-coated glass fiber facer, 18-inch ribbon, sample number 2. So let's just kind of recap or summarize that. Again, we tested 18 full-sized 4-foot by 4-foot adhered specimens with 2 facer types, and there were 3 specimens each at 6, 12, and 18-inch ribbon spacings. The specimens were typically 4 to 6 days aged at the time of testing in our lab, and the conditions within our lab space were approximately 70 degrees Fahrenheit and 30% relative humidity. So here's a table showing the test results for polymer-coated glass fiber facers. Again, you can see there's 3 of each. So the 16-inch ribbon spacings had pounds per square foot strengths varying from 624 to 719 pounds, or a difference of 95 pounds per square foot, for an average test strength of 674 pounds per square foot. And that's a coefficient of variation of 7.1%. For the 12-inch ribbons, we varied from 426 pounds to 555 pounds, which is a difference of 129 pounds per square foot. So the average test strength for that, for 12-inch ribbons, were 497 pounds per square foot, and that equated to a coefficient of variation of 13.1%. For the 18-inch ribbon spacings, we ranged from 329 pounds to 351 pounds, or a difference of 22 pounds per square foot. Average test strength was 342 pounds per square foot, fairly tight there, and a tight coefficient of variation of 3.4%. But all those coefficients of variations are reasonable and we consider to be good coefficient of variation. For the cellulosic felt facers, or B designated samples, again, with the 6-inch ribbon spacings, we varied from 558 pounds to 643 pounds, for a difference of 85 pounds per square foot. So the average test strength was 614 pounds per square foot, with a coefficient of variation of 7.9%. For the 12-inch ribbon spacings, we varied from 354 pounds per square foot to 426 pounds per square foot, or a difference of 72 pounds per square foot between the 3 samples, and that's an average test strength of 379 pounds per square foot and coefficient of variation of 10.7%. For the 18-inch ribbons, we varied from 274 pounds per square foot to 347 pounds per square foot, with an average of 307 pounds per square foot, or a coefficient of variation of 11.9%. So this slide here shows really in tabular form the test results, and on the right, in a graph form, you could see on the graph on the right, just to recap there, we have ribbon spacings that are shown along the horizontal axis there, spacings from 4 to 20 inches apart, and then on the vertical axis from a load of in pounds per square foot from 200 to 800, with an incremental division of 75 pounds per horizontal line, or pounds per square foot per horizontal line. And you can see the dots there are the actual plotted numbers that we had for each of the test specimens. And the lines we call the fit curve because they're fairly uniform and they're relatively parallel to one another. And so our testing found that there's a very strong relationship between strength and ribbon spacing. The measured direct tension strength would increase as the adhesive foam ribbon spacing decreased for both facer types. The ribbon spacing and uplift strengths represent a fit curve for the 9 data points. There were 9 data points, right? 9 of each facer type, or 18 samples total. And the polymer-coated glass fiber-faced insulation was stronger than the cellulosic felt-faced insulation boards. It was 9% stronger at the 6-inch spacing, ribbon spacing, 25% stronger at the 12-inch ribbon spacing, and 10% stronger at the 18-inch ribbon spacing. So here's a video of after we tested each sample to failure, showing that we would take the samples out and we put them onto a table that we could document the conditions and failed conditions, both photographically and visually, and as showing the various types of failures that occurred. And there's an example of a cellulosic felt-faced board. Let me just back up, and I guess I'll play that again. Again, we're taking it apart after the load has been documented at failure. You see them separating it, and then we would take each specimen out like this, unfold it like a book, and use that lift on the left side, as you can see, so we can get a nice aerial shot to document the findings. There's a close-up of the facer, cellulosic facer, and you can see the ribbon spacings here where it's peeled off in the testing. So the primary failure planes that we found were delamination and separation of the facer from the insulation, and failure within the polyiso body of the board itself. And shown here, circled in red, would be the foam separating internally. We did not ever have any failures in the low-rise foam adhesive itself, only in the facing of the insulation and the foam body of the insulation. And typically, the failures in the foam body were always at the higher loads. So here's an example in this photograph. This is Specimen A, polymer-coated glass fiber facer, 12-inch ribbon spacing, sample number 2. And you could see the entire facer is visible, and we were seeing remnants of the polyiso insulation separated and pulled apart internally. In this particular sample, we had a failure load of 555 pounds per square foot. Here's another example. This is a Specimen A6-2, again a polymer-coated fiberglass face specimen, 6-inch ribbon spacing. And because we had a closer spacing, we had a higher load. And this particular load failure was at 682 pounds per square foot. And you could see how pulled apart and separated the foam core or foam body of the insulation occurred. And again, no failures at all in the low-rise foam adhesive that was used to adhere the insulation together. Here is a shot of cellulosic felt specimen with 12-inch ribbon spacing. You can see separation of the facer from the foam body on the insulation board. On the left-hand side of the test specimen there, where I'm kind of got my head down and looking in there, lining up with my hand, you could see that the flattened low-rise foam adhesive ribbon remained in place, but the felt facer itself separated off of the adhesive, what we would term then to be like a cohesive failure plane within the cellulosic felt facer. We performed testing on smaller sample specimens, 12 by 12 samples, to check the results against the full 4-sized 4-foot by 4-foot specimens. And we also tested low-rise foam adhesive itself to measure the strength of the adhesive. So here's a slide showing a sample of what we did with the 12 by 12 specimens. They were 12-inch by 12-inch specimens. They were very much like the 4 by 4, just smaller, but they had a single ribbon placed in the center line of the sample, and they had the same T-nut configuration through the plywood for use in being able to test in a tensile machine. But we did this in a different test device, as will be seen in a slide or two here. And then we also tested the low-rise foam adhesive on what we termed aluminum pucks. And here's a photograph of it. So the foam adhesive, to measure the strength of low-rise foam, we used specially configured aluminum pucks. These are 2 inches in diameter pucks that have a smooth machine face on one side and a threaded hole on the center of the other side that were there to receive a threaded rod for use in putting in direct tension testing. And then we also tested, we tested 2 types of pucks. One, we tested 1/8-inch separated gap space between the pucks, and we did that because we noticed when we fabricated the samples, the 4x4 samples, that when we applied the buckets of weighted buckets to the sample, we would end up with about approximately an 1/8-inch thick adhesive, flattened from the weight. And so we thought that would be good. So we devised a jig that we created that would create a gap space between the pucks so that when we applied the adhesive, it would be representative of the actual 4-foot by 4-foot specimen. And then we also just tested the adhesive itself, and just by placing the pucks and a weight on top, that would end up being a very thin layer of adhesive, typically less than 1/16 of an inch. And we tested that as well. So here on the left, we have a view of the 12-inch square specimen position being tested on what we call our Citing test machine. And on the right, the 2-inch diameter puck with low-rise foam adhesive gapped at 1/8 of an inch. And as I mentioned, we made that 1/8-inch gap space to represent what we observed as being common and typical for the flattened condition of the adhesive after the weighted buckets were applied. So here's what we found in our testing for the companion 12 by 12 specimens. We tested 3 of each type. For the polymer-coated specimens, we had a strength that averaged from 660 pounds to 700 pounds per square foot, with an average of 673 PSF. And that was a fairly tight coefficient of variation. But for the cellulosic samples B1 through B3, we had a high variability. We had a load varying from 435 pounds per square foot all the way up to 660 pounds per square foot. And that's a pretty high coefficient of variation. And it underscored, I think, one reason why it was a good idea to test the full 4-foot by 4-foot size specimens. Then just to check ourselves, we wanted to just test, what if we made a full coverage specimen? In other words, not a ribbon, but we completely covered the entire 12 by 12 area with low-rise foam adhesive, and we did that for one sample. Those samples called FCA would be full coverage of the polymer-coated A specimen, and that was 896 pounds for that one sample, and full coverage B was the cellulosic, 838 pounds per square foot. For the companion puck, the companion test for the pucks with the 1/8-inch thick adhesive, we had some interesting results. We tested at 2 days and then at 5 days aging, and because the diameter of the pucks and the way the test machine works on the Citing, those test results were measured in pounds per square inch. So, for example, the TBS 1 and 2, right, they're 11.4, 11.1 PSI, respectively. that equates to a average pounds per square foot of 1,354 pounds per square foot, with a coefficient of variation of 33.9%, because we have an outlier there that was 5.7%. And then for the 5-day specimens, you could see that the PSI strength went up significantly by more than 2 times at 3,365 pounds per square foot. And these are given again in PSI versus PSF, because all of the measurements made in our testing of the 4x4 samples were in pounds per square foot. So we converted over to have this be in the same units as the strength in pounds per square foot that we were just talking about in all the previous slides here. And then the puck that was the less than 16-inch thick adhesive measured 295 psi, and it shows that the average, or the, I'm sorry, not the average, but the strength of 42,480 pounds per square foot. So let's discuss the findings and significance of these test results. The measured loads were relatively high and indicative of a good application, because the adhesive ribbons were fully mobilized. And by that I mean those weighted buckets make a big difference in being able to get a full spread and contact of that low-rise foam adhesive to the facing skin of the insulation. And when you do that, you will optimize the performance of the strength of the insulation bond. Again, keep in mind that these measured loads don't include any safety factors, although they were high, which would need to be applied. The polymer-coated glass fiber facers exhibited higher strength than the cellulosic facers for the tested materials, as shown in the graph on the right. So just to give an example, what would be like a typical uplift strength for, let's say, an average building in the Midwest? Well, that answer to that question involves a lot of different variables that need to be considered and factored in. Things like the height of the building's geometry, the type of edge detail it has, whether it is a parapet wall or not, the use of the building, topography, risk factors, others, just to name a few of the variables. So for, let's say, a small building under 60 feet tall in the Midwest, the service load, uplift service load might be anywhere between 15 to 50 pounds per square foot. And then perhaps 30 to 90 pounds per square foot or greater for a building that's taller than 60 feet. The bond strength, failure of the specimens primarily occurred at 2 planes or locations. The first type location was at the plane of the facer with the foam body, and failure at the plane was delamination and separation of the insulation board facer from the foam core. The second type failure that occurred was at failures within the foam core itself. The low-rise adhesive itself never failed, either within the adhesive or at any interfaces with the facers. And that was the case for all 18 specimens. So the adhesive strength of the polymer-coated fiberglass facers to the foam core was much more consistent compared to the cellulosic face specimens tested. And the strengths that we measured were significantly greater than typical uplift ratings for roofing systems. But again, there are no safety factors applied to those loads that were measured. The strength testing of the 12 by 12 inch companion specimens didn't correlate well with the full-size specimens. You remember that slide where we had like a coefficient of variation of, I think, 33 or 4%. The testing of the full-sized 4x4 specimens were judged to provide much more realistic and representative data than the smaller specimens. For the foam adhesive tested with the aluminum pucks, we had strengths greater than 2.5 times. From age, it shows that the increase by going from 2 days to 5 days, the strength increased by 2.5 times or greater. But the testing was minimal when we tested just adhesive by itself, thickness, minimal thickness of adhesive by itself, but it produced really significantly greater strengths compared to the 1/8-inch thick tested specimens. Again, this underscores the importance of weighing down the boards during installation to allow for lateral spread of the adhesive to get as wide of a contact area as possible so that you can get the optimal strength. Some of the limitations we had with the testing that we performed, we want to point those out. All of the test information was derived from one manufacturer's product for both the insulation and the adhesive. And the number of duplicative samples, which was 18, presents some limitations in performing a statistical analysis to be able to interpolate for use for roofing systems or assemblies. Because we only tested one component of the typical roof system, right, the insulation bond to insulation. So this data is not the same as values for like a full system, roofing system, which would include a cover board and the membrane and other components like the vapor retarder that may be present in the assembly. We'd like to continue doing some testing to include and recognize factors that can affect adhesive strength and that weren't studied, such as temperature and moisture ranges, the differences of temperature and moisture, surface contamination, and what influence or impact that would have on the testing. Obviously, would bring it down some, but we'd like to know what would be tolerable. The insulation thickness was 2 inches. We don't know if there's any difference between 1 inch and 3 inch, for example, and we like to be able to check that and see that. Consistency and amount of ballasting panels. Pat mentioned that we used 26 pounds because that was the recommendation, I think, from the manufacturer that we used, and it was subtracted from the weight of the plywood, etc. But what influence does that have on getting these results? Obviously, we know from the testing made that if we can mobilize that adhesive by making the maximum contact of the adhesive to the facer, we will achieve the maximum spread. But the revelation was that it's not really the adhesive that fails ever. It's the insulation itself. The facer delaminates, or the core, a foam core or bodies, is the limiting factor for failure. And we'd like to be able to test and check moisture within the substrate as a possibility and factor too. For example, concrete, duct moisture. So, in summary, we need to consider the test data and synthesize the information with design and installation practices. So you need to review ribbon spacings and tested roof systems, and also review the need and required factors of safety for uplift performance. And it would be good to evaluate and test multiple manufacturers' insulation products and adhesive products, because again, we only tested one manufacturer's product and adhesive. So that concludes the presentation, and at this time we'd like to open it up for questions.
Thank you, Rich.
Turn this back over to Liz.
Yeah, thank you, Rich, and thank you, Pat, for the presentation. As a reminder, you can type your questions into the Q&A box and hit submit. We'll try to get to all the questions during the call, but if we aren't able to get to your questions today, then Rich and Pat will follow up with you afterward. Okay, let's take our first question. Why did you test 4-foot specimens? Doesn't the industry use 2 feet in the field?
I'll take that one, Liz. So first of all, the MRCA asked that if we could test full-size specimens. That was a question in their problem statement, and we thought that was a good idea. We didn't want to deviate that, and we weren't. We knew that there are standards for 2 foot that the Pat cited, for example, the ANSI FM standards. We were aware of those and used those, but we felt that with the 4-foot specimens, we could negate any influence that would have from, for example, a tripod is typically used, and so there's some influence of self-reacting forces in that test frame, and we didn't have any of that. Plus, we tested 4 by 4, 16 square feet versus 4 square feet, so we tested so much more area. We think that's more indicative. More areas, we were able to see more of the ribbon space used. Right, it was more than just one ribbon, and we think that made a difference for us in our testing. I hope that answers
our next question.
Okay.
So this next question starts, I'm sorry if you already noted this, but did you test the same thicknesses of insulation or varying thicknesses?
I'll take that. We tested just 2-inch. It's a very common thickness of insulation that's used in the industry. So that 2-inch was the only thickness that was tested. Would be interesting to see what the, if we were to use thinner, thickness insulation or thicker and see what those results are.
Okay, our next question. How does the PSS of resistance relate to wind uplift design factors?
I'll take that. Well, again, the building codes, each building is different. It's got its own unique geographic location, and so there's a formula that is used, and all those factors are determined. But wind, including wind speeds, are provided in the building code, and there is an equation that you have to go through to calculate these loads. It's pretty involved, and but the building code prescribes what and how to determine that. And what we find whenever we do a roofing project, if we're either designing one or doing a replacement design, we always check the wind uplift load required for that site, and use that in our specifications.
Okay, our next question. I'm in Chicago. We're commonly installing roofs in 40 to 45 degree temperatures, which affect the foam adhesive. Do you plan on replicating this test on the lower end of the recommended roofing installation temperature range?
I'll take that. That's a great question, and that is something that we are discussing right now with MRCA. We think that's an important thing to check for and test. Obviously, didn't test for it in this study here, but we think it's a good subject to test and to look into, and we plan to do that in the future.
Okay, our next question. My takeaway from this is that ribbon installation in the field should be maintained at the 3/4 inch size to be spread as thin as possible. I would assume that if we see globs being installed, we should consider that wrong.
I'll take that. I think maintaining the 3/4 inch to 1 inch thickness that the ribbon thickness that the manufacturers recommend is good. I think what's important is to make sure that you're getting that weight on the insulation and allowing that adhesive to spread to get that maximum bond on the facers for the insulation.
Okay, next question. What was the criteria for failure? Was it the separation of the insulation panels? Was the separation of the insulation panels a certain distance, or was it complete failure?
I'll take that. Well, we weren't really looking for criteria for failure per se. We tested the failure and made measurements and observations of where the failure plane was. What was the second part of the question?
I believe the question is, was it considered failure if the insulation panels separated by a certain distance, or were you looking for a total failure?
we measured, failure was defined as when the load was no longer sustainable. In other words, when we, let's say, for example, tested to 600 pounds per square foot, and then we could not apply any more load. We could visually see a separation that occurred, and then we had a quick drop-off in the measured load. We couldn't apply any more force, essentially. That was our maximum load at failure. And then, again, by having that center yoke, we were constantly measuring deflections to see that we were getting a nice uniform pull. We did for all 18 pretty uniformly because we measured those transducer loads, which are not given in this presentation, but we did record and provided in the report to the MRCA. That was important during testing for us to be able to check and monitor that. But the center yoke was really the key in being able to get a nice uniform pull that didn't really peel or pry from one end or the other. So the failures that occurred as a result of a uniform pull. And if in some locations we had peeling of the facer versus foam core and body, that occurred just naturally because we did provide a consistently uniform direct tension pull that did not have any prying action.
Okay, we've probably got time for one more question. Would you recommend different adhesive spacing for different facers or insulation densities depending on their failure rate / points?
I don't think we're recommending changing the spacing that's required by the manufacturers, but I think it's interesting that insulation densities could be another avenue for testing in the future.
Right.
Okay.
Yeah.
Rich, would you like to add something?
No, I mean, I agree. I think that the insulation densities is important, but it does underscore and show that, again, the limiting factor here is the insulation is really the weak link in the system. It's not the low-rise foam adhesive. It's the insulation. And so by spacing the variable ribbon spacing apart, we know, for example, from, and this, we don't want to deviate from what the manufacturers say, but at 4-inch ribbon spacing, you're almost doing full coverage, I would say, because you get a spread of 3 inches or 3.5 inches by using weighted buckets. That's about what the flattened surface of a typical bead of adhesive. Of course, there's variability in that number that I just said, but you get around a 3-inch wide spread by putting these weighted buckets down. And if you did that 4-inch ribbon spacings, you're almost getting full coverage of adhesive. And maybe you want that in some cases, and maybe it's unnecessary in others.
Okay, that is all the time that we have for questions today. Like I said, if we didn't get to your question, Rich or Pat will follow up with you. But thank you so much for joining us today, and thank you, Pat and Rich, for the presentation. We hope it's been educational. If you have any questions about the presentation today, please don't hesitate to reach out to Pat or to Rich. Their contact information is on the screen. And if you have any questions about WJE webinars, please contact me, Liz Pemper, at lpemper@wje.com. So again, thank you so much for your time, and we hope you have a great rest of the day.